Hello, Calculus. This video will be viewed after Friday's class, before Monday's class, and Friday is the 4th of November. We're going to be looking at Rolle's theorem. It is often taught after the extreme value theorem. And the extreme value theorem, you'll recall, says that for a continuous function on a closed interval, there must be both a minimum and a maximum on that interval. So both of the values, though, for the mean extreme value theorem could occur at the endpoints, and we check for the absolute max and min by looking at the endpoints and those places where the derivative either equals 0 or doesn't exist. So what Rolle's theorem does, though, is he's going to give conditions that guarantee the existence of an extreme value in the interior of the closed interval, not at the endpoints. Let's write down Rolle's theorem while I go on. You can pause the video. I'll read it. Rolle's theorem says, let f be continuous on the closed interval a to b and differentiable on the open interval a to b. It really doesn't make any sense to be continuous and differentiable on a closed interval, because then we would have endpoints where we would try to draw derivatives. And derivatives, the slope at an endpoint cannot be drawn. We wouldn't know which way to draw the tangent line to observe its slope. So that's why we have to indicate differentiability is on the open interval. So if f of a equals f of b, then there is at least one number c in AB such that f prime at c equals 0. So you write that down and then turn me back on and I will blab on about it. So let's take a minute and think of what this means with a picture. Then we'll do a problem or two or three to indicate how it works algebraically as well. So we will look at a picture where the function is continuous and differentiable, and then we will look at one of the stipulations here is f of a equals f of b. So that's what I'm going to draw now. So I'm going to give it a and say its value for the function is right there, and say that's at 5. And b, the value of the function at b must be equal to the value of the function at a. So this function has to go through these 2 points. And normally we have the name of the function, but theoretically right now we don't. So we know the function has to go through this point, and it's continuous, so there's no jumps, skips, hops, holes, etc., asymptotes. So it could look like that, or it could look like this, or it could look like this. We really have no idea, but we do know the function goes through this point and this point. When that's true, and it is a continuous function differentiable on the closed interval, then there is at least one number c in between a and b such that the derivative is 0. So that happens at a mountaintop and a valley. So they're guaranteeing, Rolle's theorem guarantees that there is going to be a slope of 0, a derivative that's 0, somewhere between. Maybe here, if it's this function, and look, if it's this function, we have lots of 0 derivatives, but Rolle says there has to be at least one. So, thinking of it this way, say f of a equals f of b. Can you think of a way to draw a function, a line, a continuous line from a to b where the derivative does not equal 0, where there's no place where the derivative zeroes out. So you might try going like that, as I said, but that has a spot here where the derivative is 0. You might try going down, but that has a spot where the derivative is 0. So then you'll really try to outwit Rolle's by going straight across. But here the derivative is 0 everywhere, so there's an infinite number of places where the derivative equals 0. Rolle says there at least one. All right, geometrically, this should make sense to you. So let's look at an example. Let's look at f of x equals x squared minus 5x plus 4 on the interval from 1 to 4. When we look at that, first of all, we have to ask if it meets the conditions. Is it continuous? Always ask yourself that. Well, this is a polynomial. It happens to be a parabola. So any polynomial has variables and coefficients. The coefficients are real numbers. The exponents are integers, and I forget all I forget the particulars about the polynomial. So let me clear that up for you. I think the exponents have to be whole numbers and the coefficients have to be real numbers. But this is a polynomial. It is a parabola. It is continuous everywhere in this interval. Is it differentiable? In the closed interval, not in the closed interval, in the open interval from 1 to 4. Because it would have endpoints, if we close the interval there, we couldn't find derivatives at the endpoints. So when we have an open interval, that is no longer a problem. So let's look at the derivative. And that is everywhere. This one has no mathematical impossibilities. It is always differentiable. All right, so it passed the two requirements. Yes, it's continuous. Yes, it's differentiable. So now we just have to see if f of a equals f of b. So in this case, f of 1, does that equal f of 4? Well, if you plug 1 into this expression, you get 1 minus 5 plus 4, you get 0. And when you plug 4 in, you get 16 minus 20 plus 4, which you also get 0. Now, these do not have to be 0. Like up here, I said f of a was 5 and f of b was 5. They do have to be equal, but they don't have to be 0. This one did turn out to be both equal to 0. So once you meet all those requirements, then you can say that there is at least one number in this between 1 and 4 where there is a derivative that is 0. And that's what Rolle says. Now he doesn't, it's an existence theorem. All he's saying that such a number exists. He guarantees it. But he does not tell you what it is or how to get it. However, we have a brain, so we're able to do that. So let's go beyond what Rolle's guarantees it. Now we'll find it. So what is the value between 1 and 4 that this function has a derivative of 0? So well, we already found the derivative. Let's set it equal to 0 and solve for the value for x where the derivative is 0. So I get 5/2. So at 2.5, is that in the interval of interest? Yes, it is. Rolle's it guaranteed this value existed, and we went beyond rolls and found out what it was. So at the value x equals 5/2, this function has a derivative of 0. It's a mountaintop or a valley. All right, so let's look at another one. Let's look at f of x equals x squared minus 1 over x between -1 and 1 in this interval. And this one, it turns out that we have to ask the question, is it continuous on that interval? And the answer is no, it is not, because we cannot have a value of x equals 0, because that would create a denominator of 0. So therefore, this is not a continuous function everywhere in this interval. So therefore, we cannot use Rolle's theorem. It does not apply to this particular problem. And let's see if you can try one. You try this one. You try f of x equals x to the 4th minus 2x squared on the open interval minus 2 to 2. So I want just to find out if Rolle's theorem applies. So answer, is it continuous? Is it differentiable in the interval of interest here? And if so, go beyond Rolle's and find those spots. So go ahead and find those spots that Rolle's theorem guarantees, and I will check with you on Monday to see how you did on that problem, and then you'll have a taste of what kind of problems we'll be looking at during class on Monday. All right, so you can roll with that. See you on Monday.